Hello, today we are presenting semi-supervised active learning for video action detection done by a team from IIT ISM and CRCV at University of Central Florida. Some of the challenges for video action detection include annotation cost for large video dataset, as videos have multiple frames which require spatio-temporal annotation, the overall cost for dense dataset goes up. Similarly, it's important to identify the helpful samples for annotation as unrelated samples eat up the budget, while repetitive samples prove to be redundant for the training process. Finally, as we have small labeled dataset to start from, we run into cold start problem, and the quality of pseudo labels with small labels also affect the training process. Prior work in this regard uses model-driven active learning, where the model is perturbed during the active learning cycle. However, the amount of perturbation for model is limited as the performance quickly degrades as we add more perturbation. Other works that use data-driven active learning do augmentation on the data during the selection process. This gives more control over the regularization of data. However, due to the augmentation being similar during training and active learning process, there's some bias which hurts the performance. Finally, conforming to other SSL approach, we have cold start issue where sparse data with few labels in the beginning phase causes the model to not train properly. This results in prior work assuming that the sparse data available in the beginning is larger, thus requiring larger annotation cost. So our motivation for this paper is to first reduce the cold start issue. For this, we use both the labeled and unlabeled dataset in an effective way so that the initial model can be trained with low sparse label data. Then we want to improve the training process by making sure that the pseudo labels that are generated and used in the training part is more effective. So our approach focuses on improving pseudo-label use quality. And we also want to improve the active learning selection process. And for this, we want to reduce the bias during training and selection process. So we use a separate type of augmentation for active learning selection, which allows us to do effective perturbation to identify the most useful sample that should be annotated in the next round. So our contributions are as follows. First, we propose a noise-based augmentation approach called NoiseAug during the active learning selection step. Here we add Gaussian noise to perturb each frame and get the variance of uncertainty to rank each sample and identify the top samples the model fails in. Then for the training part, we propose a FFT attention approach to improve the pseudo label for training. We identify high frequency areas in the pseudo label by passing it through a high pass filter. We hypothesize that the edges are the areas where the model fails more. So if we improve the edges, the overall quality will also improve. And we measure the consistency between the edges from different augmentations. Finally, we also ensure that there is some temporal consistency for video prediction, as the noise level during prediction should not deviate a lot temporally for the same location. Here is an overview of our proposed approach for the training. We take the labeled and unlabeled data and pass them through strong and weak augmentation following the teacher-student training method. When we get output for different augmented variations, for label data, we compute classification and detection loss using the supervised loss formulation. And for the unlabeled data, we pass it through a high-pass filter to find the FFT mask. That's the mask for the potential edges. And we use this mask as a weighted parameter to compute the consistency loss between the different augmented variations. For the consistency loss, we use the following formulation. First, we get the frame-wise consistency, which is MSE loss between the student and teacher network's output. Then, since we want to focus only on the high frequency area, we get the mask using HPF function and get the frame-wise consistency between the different variations or augmentations of the same input that's given from the student and teacher models output. Once we get the consistency for these variations using the corresponding FFT mask, we compute the overall loss where we use a lambda term to adjust the weight for the semi-supervised consistency loss. As for the active learning selection step, we take the unlabeled video and perform noise augmentation where we add a Gaussian noise to each pixel of the frames for that sample. We use R augmentations, which is 8 in our case, and pass it through the trained model. This trained model is the student model from the training process. Once we get the output from all the augmentation, we average the uncertainty score and rank the videos and select top K for annotation in the next round. Our experiments are done on UCF 101 for 24 action classes, GHMDB for 21 action classes, and we show generalization on YouTube VOS dataset. Here we show comparison with prior works. We show it for UCF 101 with 24 classes and GHMDB with 21 classes. We compare with fully supervised approach using both 2D and 3D convolution backbones. Fully supervised approach use 100% of the annotation. Similarly, we compare with weakly supervised approach. These use partial annotation, and semi-supervised approach, which also use partial annotation at a given percentage. Compared to all of the prior approaches and the supervised baseline using the same backbone, our approach, shown here in green with mean teacher semi-supervised learning and mean teacher semi-supervised learning plus the proposed active learning, shows improvement over all prior semi and weakly supervised approach. And we also notice that with active learning, the overall performance improves quite a lot compared to without active learning approach. Next, we show active learning selection analysis, where we show the comparison between different active learning selection approach, such as uncertainty approach, entropy based approach, and random selection to compare with ours. And here's also the 100% supervised baseline. We show it for UCF 101 on the left two and GHMDB on the right two graphs. We observe on the green line that noise augmentation, which is our selection approach, consistently outperforms all the previous active learning selection approaches. This is confirming that the bias from augmentation during training is not carried over as much compared to prior works, as well as having temporal consistency also gives better performance on the selection process. Similarly, we showed the training analysis of different kind of SSL approach on UCF 101 and GHMDB at different annotation percent. We saw just consistency based training, mean teacher based approach, and our mean teacher plus high frequency filter approach. And we consistently see that using FFT improves on just using mean teacher and is a better semi-supervised training method. Here we show what the FFT filter sees. As we observe on some of the samples, the blue is the detection region and the red is the background, and the edges as highlighted here are detected where we give more weight. So blue and red gets less weight compared to the edges during the consistency computation. Here we show the effect of different degree of noise in the noise log for active learning selection. As we add more steps and get higher percentage of annotation, we notice medium noise with given standard deviation performs best compared to high and low standard deviation noise. Thank you for attending our presentation. Here's the project link and the QR code where you can get more details and materials about this project.